This is K Devender Reddy, Assistant Professor in Institute of Aeronautical Engineering, EEE Department. In this video, we are going to discuss about rotating magnetic field, RMF. So, generally, the three-phase AC machines require a rotating magnetic field. So, before actually discussing about what is the need of rotating magnetic field, first we should discuss about what is a magnetic field and how we will develop the magnetic field in the machine. So magnetic field generally it is an imaginary lines of forces which have attraction or repulsion forces in that particular area. We can call it as a magnetic field and magnetic field area. So we can produce a magnetic field with a DC supply, and we can also produce with a single phase AC supply and three phase AC supply also. But the nature of the magnetic field is different. When you excite a coil with a DC supply, it produces a constant magnitude stationary magnetic field. It is not revolving, it is a stationary magnetic field is developed. When you excite the single phase winding with a single phase supply, it produces an alternating flux or alternating magnetic field. The magnetic field is keep on changing from positive maximum to the negative maximum and then reaches to the zero. It is an alternating or pulsation magnetic field. You can also produce a magnetic field with a two-phase, two-winding system, and we can also produce a magnetic field with a three-phase, three-winding system. But in the case of the AC machines, specifically a three-phase machines, we need a rotating magnetic field because where the conductor is stationary. To satisfy the Faraday's laws, we need to satisfy the Faraday's laws. Either conductor has to rotate or magnetic field has to rotate or change. So the Faraday's laws says the induced EMF is proportional to rate of change of flux cutting or rate of change of flux linkage with the conductor. So in this case, in the case of the AC machines, there is a possibility to satisfy the Faraday's laws. One possibility to rotate the conductor, and another possibility either to rotate magnetic field. So in this context, we are discussing about how the magnetic field is revolving or rotating, and is it a constant magnitude revolving magnetic field or variable magnitude revolving field or rotating field. We will discuss in this video. When a balanced three-phase or a polyphase current, a balanced three-phase supply is connected to a three-phase windings, whether it is a star or delta connected. For example, I am assuming when a balanced three-phase supply is connected to a star connected three-phase winding, it will produce a rotating magnetic field with a constant magnitude. In this case, a balanced three-phase supply is connected to a star connected three-phase windings. The star connected three-phase windings each will be 120 degrees apart. Let it be some A phase, some B phase, and naming as a C phase, which are specially 120 degrees apart. Here in this picture, in this slide, I am showing the respective three-phase waveform, sinusoidal waveform. So the phase A starts from origin, that is a 0, and reaches the maximum point and then reaches to the negative 1. Similarly, B phase, which starts negative, that is delayed by 120 degree lagging, and another one is also delayed by 120 degree or 240 degree. The general requirements to be satisfied for producing a rotating magnetic field. The three-phase winding must be physically displaced by 120 degrees, electrical in space, The mathematical representation of the flux produced by these three phases, that is respectively I am naming as R, Y and B, that is phi R flux produced by R phase, that is 5m into sine omega t, flux maximum, the magnitude of flux developed into sine omega t, phi y, that is the flux produced by Y phase, is phi m sine omega t minus 120 degree, and flux produced by a B phase is phi m sine omega t minus 240 degree. The three phase currents flowing through the above three windings must be time displaced by 120 degrees electrical. The vector sum of the currents, these three currents in a balanced three phase system, it must be zero at any time instant. The sum of these three in a balanced three phase system, it must be zero at any instant. But the resultant of the magnetic fields produced by the currents is not zero, rather it will have a constant magnitude, non-zero value, and it is rotating in space with respect to the time. The vector sum of the three currents in a balanced system is zero at any instant, but in the case the resultant of the magnetic field produced by these three currents will not be the zero, and it will be a constant magnitude value, and it is rotating in a space with respect to the time. The magnetic field produced by the current in each phase can be represented by the equation given below. This is a similar representation of currents as we discussed in a previous slide in a three-phase system, as the flux is a cofacial with the current. So phi r equal to phi m sine omega t, and where phi r, phi y and phi b are the instantaneous fluxes of corresponding R, Y and B phases, and phi m represents where phi m is the amplitude of flux wave. The flux wave in the space can be represented as shown in below figure with the three different colors, red and yellow as well as the blue color. And here I am assuming a three instant 0 at instant 0, that is at A R phase starting point at origin, then instant 1, instant 2, 3 and 4. I am considering the 4 instants. In this 4 instants of time, I am analyzing how the magnetic field is rotating, or how the magnetic field is a time variant, and is the magnetic field produced by the three phase balanced AC system is constant or not. Now on the graphical representation of the flux waves, we will first consider the point 0. In that case, phi r equal to phi m sine omega t, that omega t becomes 0, it is equal to 0. Here the value of phi r is become now 0. Next, value of phi y, that is equal to phi m sine omega t minus 120 degree. So here omega t is a 0, I am substituting, and phi m sine minus 120, that represents minus square root of 3 by 2 phi m. The value of phi b phase flux, equal to phi m sine omega t minus 240 degree. So it is square root of root 3 by 2 phi maximum. The resultant of these fluxes at the instant, means at that instant, 0 instant, resultant flux is 1.5 times of the maximum flux. You can see here the representation, that is a picture representation. This is your y phase, sorry, negative y, that is, this is y1, let us assume it is y2, and this is y2, and this is y1, and it is b phase, and opposite content is and this is r phase. 3r spatially displaced by 120 degree, and this will be shows the negative value of y axis, that is minus root 3 by 2 phi m, and this is r phase, so resultant phase. So resultant is a vector sum of these two, b phase as well as the y phase. You will get resultant of these two will be phi maximum. Now in the similar way, we'll consider the second point, that is instant 1. where omega t equal to 5 by 6, that is 30 degree. At the 30 degree instant I am considering. Here the value of phi r is equal to phi m omega t. Now it is 30 degree, it will be 1 by 2 phi m, 0.5 phi m. The value of phi b, similarly substitute your omega t equal to 30 degree, you will get minus phi m, and the value of phi b, it is equal to similarly half, 1 by 2 phi m. So here this is B phase, which is of 1 by 2 phi m. This is 1 by 2 phi m, and R phase also 1 by 2 phi m, and B phase 1 by 2 phi m, and value of Y phase is minus phi m. So now the vector combination of these three will gives you resultant flux I phi r equal to 1.5 times of maximum flux. And similarly, the another case, when point 0.2 instant omega t equal to 5 by 3, that is a 60 degree. Similarly, the resultant flux will be 1.5 times of the maximum flux which produced. And similarly, consider one more instant, point 0.3, where omega t equal to 90 degree. Then substitute in the previous expressions phi r, phi y, and phi b, and similarly you will get 1.5 times of the maximum flux, which is shown in the below figure. Here it is clear that a resultant flux vector is rotated 30 degree further in a clockwise direction. In each instant, it is rotating in a clockwise direction 30 degrees without changing its maximum value or without changing its amplitude. In this way, we can prove that due to balanced supply applied to a three-phase stator winding, rotating or revolving magnetic field established in the space. The magnitude of rotating magnetic field produced by a three-phase windings and three-phase currents is 1.5 times of the maximum flux, and where the phi m is the maximum flux, which will be flux density which will be produced in any phase, and the speed of the rotating magnetic field is 120 f by p rpm. It is called a synchronous speed of the rotating magnetic field, which will be produced by a balanced three-phase AC supply is connected to a star connected three-phase windings. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.